So let us start today the oscillatory motion for damped vibration. That means let us consider the case of light damping. Okay, why light damping? Because now we are considering the case of K less than omega naught. So this we are calling as light damping. Okay, what happens when we do light, when we give light very little bit of damping? All right, you will see then square root of k square minus omega 0 square. This square root becomes an imaginary quantity, isn't it? Because if k is less than omega, then this value will become negative. Under root negative is an imaginary quantity. So this becomes an imaginary quantity. So just by invoking this condition, you are introducing an I in your equation. So this becomes an imaginary quantity. So let your, well, k square minus omega square be equal to I omega prime. So let us consider square root of k square minus omega 0 square as equal to, well, I omega prime. Okay, or what would you say over here? Or omega prime is equal to square root of omega 0 square minus k square. Okay, so what will we write the solution now? Well, the solution will write as, you will see, we'll write the solution as, well, y equal to e to the power minus kt, okay, into, if you remember the solution of yesterday, a1 e to the power I omega prime t plus a2 e to the power minus I omega prime t. Okay, so this is what we are getting. So what do we do now? We put say a1, this is already you see that we have invoked the condition of a sine cos function has come in. Just by considering the situation of light damping, a sine cos function has come in. So what do we do now? We put a1 equal to, it's a mere substitution, we do it as a0 by twice I e to the power I5. Now, various books will have various kinds of methods. You can follow any method which you think convenient. Okay, this is one method that I am following. Okay, and A2 is equal to A0 by 2I e to the power minus I5. Okay, all right. Now, what is A0 and phi? So if you consider here, A0 and phi are also constants, the value of which depends on the state of motion at t equal to 0. So A0 and phi depends on the state of motion. It depends on the state of motion at t equal to 0. Okay, all right. So if you just substitute, what will you get? You see, if you substitute, you will be getting y equal to e to the power minus kt a0, okay, and then, well, e to the power I omega 0, I think it's omega, not omega 0, it is omega prime t plus phi, okay, minus e to the power minus I omega prime t plus phi. Okay, so the second bracket gets closed. The second bracket gets closed. Okay, all right. So the whole thing should be divided by 2i. All right. So that's what we get over here. All right. Close the second bracket. Okay. So you see this, if you just write down, you will see this is equal to, if you just simplify it, a0 e to the power minus kt sine of omega prime t plus phi. Okay, look at the amplitude factor now. Instead of a0 now, you have this term. So this actually, as I told you before, plays a significant role in damping. Okay, so this is the equation of a damped oscillatory simple harmonic motion, y equal to this, with this as the amplitude. So this becomes your amplitude. This is your amplitude. All right. Okay, so you see, well, the amplitude is decreasing with time. Now what is the frequency for this motion? You will see the frequency omega prime that we have over here is equal to square root of omega 0 square minus of k square. So this actually, you realize, is less than the natural frequency of the harmonic oscillator. What was omega 0 equal to? If you remember from free vibration, it is equal to square root of S by m, isn't it? Now how do we find out the value of the constants a0 and phi? So now let us find the value of, to find a0 and phi. How will you do it? How will you find it, a0 and phi? Well, you can show that when the displacement is maximum, say at y equal to y0, which is your maximum displacement, okay, that let it happen at time t, that means you are starting from that time, at time t equal to 0, so that when the displacement is maximum, dy dt is equal to 0. Okay, so well, if you substitute this in the equation, in this equation, so dy dt will be equal to 0 at t equal to 0. What we get over here is y0 is equal to a0 sine of phi. Okay, y0 is equal to a0 sine of phi. All right. Okay, so if we differentiate this equation, if you consider this as today's master equation A, so differentiating equation A, differentiating equation A, what do we get? Well, dy and of course putting dy dt equal to 0 at t equal to 0, what do we get? 0 is equal to minus of a0 k sine phi plus a0 omega prime cos phi. Okay, so you can show that, well, you can show that your, well, tan phi is equal to omega prime by k. So that is equal to square root of omega 0 square minus k square by k, and sine phi is equal to omega prime by square root of omega prime square plus k square. Okay, so if we substitute these values, okay, we get for y0, what do we get for y0 when we substitute these values? We get for y0 is equal to, well, a0 omega prime divided by square root of omega prime square plus k square. So this is actually equal to, if you just do it, you will see this is actually equal to how much? A0 omega prime by omega 0. Okay, so what is your A0? Therefore you can get your A0 from here, y0 omega 0 by omega prime. Okay, which is y0 omega 0 divided by square root of omega 0 square minus k square. Alright, so if you substitute, because later maybe you may have to do problems, then you need all the smaller terms whose values are given. So if you substitute for y, what you get? Y is equal to y0 omega 0 by square root of, well, omega 0 square minus k square e to the power minus kt sine of square root of omega 0 square minus k square plus phi. You get something like that. Okay, and if you plot it, then now because of this factor, you will see this equation. If you plot it with respect to time, the amplitude, okay, the displacement, if you try to plot, okay, if you plot y, then you will see, say from 0 to p, you are plotting this. Okay, you will see that this amplitude goes on decreasing in this manner. All right, the amplitude of oscillation goes on decreasing following the condition a equal to a0 e to the power minus kt. Okay, so let's stop over here. All right, okay, and if you have any queries, please come forward with it.